So our third speaker of the day is Shaoshi Chen from the Chinese Academy of Sciences, and he will tell us about a residue-based approach to vanishing sums. Please, Shaoshi.
Thanks for the introduction, and also thanks to the organizer to invite me to give a talk in this nice conference in memory due to Amitai and Doron. So today I'm going to talk about how to prove a class of vanished sum using some residue techniques. And this is it's a joint work with Rong-Hua Wang, who was a student of Qinghu Hou. Let me first record some photo with Doron. So I should say thanks to Doron for his always many supports in my career. So this is a photo I think you already showed last night in the social session, and this is taken a few years ago when I give a talk in Doron's seminar. Actually, I should say Doron has his work has influenced my research a lot. And here you can see one of the data which I got from a MathSum review. There are 2,794 citations for all his works, and actually I contribute 106 in my 24 papers. And when I go to the ECM, my author profile, I see that the critical telescoping, which is Doron's top 5 paper, which is about the critical telescoping, and my keyword, this is the biggest keywords in my author profile, which you can see that how Doron influenced my work. So I should say thanks to Doron. And also I have given 3 talks at Doron's seminar. One is in when I was a postdoc at NC State. First one is 10 years ago, and then is the next when I was did my 2-year postdoc in NC State. I went visit Doron each year, and then the last one, the third one is 3 years ago in when I'm attending ISAC in New York. Then I visited Doron. So my first plan is to give a slides talk, but then I choose to give a blackboard talk, which is more traditional. So here is the photo I have. Thanks for Doron inviting me to give a talk at his seminar. And also I should, before I starting my talk, I should say happy birthday to Amitai, Professor Amitai and Professor Doron. So this is the photo I took last 2 months ago when I visited a famous mountain, and there is 4 of this word. This is mean the long life, which is this Chinese word, which is beer. Beer also can write this calligraph for Doron. And also let me wish both of you long life and happiness. So here, this is a Chinese word "so" mean long life, and happiness is this "fu." So that means say in Chinese, "fu lu donghai, so bi nan san." Okay. Okay, now let me start my my talk. I think I should give. I have been working on this topic for almost more than 10 years. I see that many talk has has connection with this double-Z method. So I should give at least give a very brief introduction or brief lecture on this theory. So this is almost 30 years ago. Wilf-Zeilberger developed an algorithmic theory for proving identities, which arising from combinatorics and special functions. So nowadays, to prove this kind of those identities become routine or mechanical. So people will not bother to really to spend time. You can just call Doron to run his algorithm to give the computer-generated proof of those identities. Let me give can anyone see this? Here I see there's a zoom line which hide part of my slides. Did anyone see my full slides, or there's some zoom hide of my slides?
No, we can see your full screen.
Oh, okay, just my slide. Okay, no problem. So the key idea in this double-Z method is so-called critical telescoping. So let me first explain what mean the telescoping. So telescoping means given a sequence in certain class, we will, in different application, we will specify this class. And then the question is how you can find another sequence which in the same class of F, so that Fk is written as difference of this Gk. We denoted it by delta Kg. And then you were curious about why we care about this kind of telescoping relation, because we can use this relation to evaluate a definite sum. For instance, if you sum Fk from A to B, then if you have this nice G, then you can get a nice formula for this definite sum. That's the telescoping. And for example, when we were in the high school, almost all students will try this to sum this, like for n equal to 2021, like this year, and then you ask the student to evaluate this. And the technique is you write the summand as difference of another rational function, which is 1 over k minus 1 over k. And then you get the gross form for this. If it's n equal to 2021, you get the formula. More challenging sum is like this. So given this summand, and then there is a algorithm so-called Gauss-Brackton can find this GK for you. And then you can evaluate this definite sum. And then you get this nice formula. So this is telescoping. But the life is not so, sometimes not so easy. Sometimes you cannot get this kind of nice G. And in this case, you need to create some, some creative idea. For instance, if the problem involves some parameter n, maybe the fnk itself cannot express as the difference of another nice G, but you can do something with respect to this parameter if you have a parameter. So then you can, if n is a shift parameter, then the natural idea is you shift those parameters and try to combine those shifts, do the linear combination so that you get the nice G. Then this linear combination of this shift is this linear recurrence operator. You will try to find this property, this nice linear recurrence operator, so that if you apply L to F, you get this a difference of another nice G. So this L is called the telescope for F, and G is called a certificate. And then, for example, if you start with take this as example, and you can check that, you can use Gauss-Brackton to check this given sequence cannot written as a difference of another nice G. But if you do something with this parameter, you do some properly the linear combination, which means if you take this first order linear operator, you apply L to F, then you can get this nice G. So this is you get a telescope L. And then you were curious about why we are bothered about computing such kind of L and G. One of the big applications is we can use this LG to prove identities. For instance, let me take one simple example. If we want to prove this identity, and the general philosophy is you first view both sides of this identity as a sequence in N. And then the first step you want to prove both sides of this identity satisfy the same recurrence. And then you try some initial values. And then you prove the identity. Now the hardest part is how you can find the linear recurrence satisfied by the left-hand side of this identity, because this involves some symbols. Then the idea is to use the creative telescoping. So now in Maple or other mathematical computer algebra system, now this is a very good algorithm, well-derived algorithm. You can compute this L and G. This will bring you this first order linear recurrence operator and also this nice G. Now you do some now you can because the nk you deal with some boundary conditions, and then you know that this finite sum actually equal to this left hand side. Now you apply this operator which is running k from infinity to positive infinity. You apply this sum operator on both sides of this red relation. Then you notice that L is the operator which involve only n. So this commutes with this operator, blue operator, sum operator. Then you can get this insight. So you notice that this is the left-hand side of this identity. Now on the right-hand side, taking this sum of the difference is quite easy. Use the previous discrete Newton-Leibniz formula, you can get this value. Very often this is equal to 0. So for this example, you get this relation. What this means, which means the left-hand side identity satisfies this linear recurrence. Let me write down the recurrence explicitly. So which means the left-hand side of this identity, now you satisfy this linear recurrence, which is coming from this telescope. Notice that this is first order, and for the right-hand side, you just plug in this recurrence to check whether the right-hand side satisfies this recurrence or not. Indeed, this satisfies this recurrence. So now you have proved that both sides satisfy the same recurrence. Since this is first order, you only need to check one initial value, then the identity is proved. So that's the idea of a WD method, how you can use telescope to prove the identities. There's more advanced example, like for instance, like you want to prove this identity. So here, this is the summand, and then you want to prove that this sum is equal to harmonic numbers. And then the idea is the same. You first compute take the summand, and then you apply some algorithms. You could bring you L and G, which is as follows. And now you take the sum K from 1 to M on both sides. For this example, there are some complications because the operator sum with respect to K is not commutative with L, but they are not so much non-commutative. There's still a remaining term is this. So in this case, what you get is a non-homogeneous recurrence. And you can also get the value of this. This is 1 over M plus 1. And once you see this recurrence, which means the right-hand side, the left-hand side, the sequence satisfies this relation. And then you notice that harmonic number also satisfies this recurrence. So now you show that both sides satisfy the same recurrence. And then you only need to check the initial values. And this is you prove the identities. I think now, after this conference, this T-shirt become very famous. If you put the eBay, the price probably now become more high. So actually, the identity from this famous T-shirt, nowadays we can also verify it with Maple one worksheet. So just write down this identity, and then you type in the Maple this summand, and then now you call the Zeilberger recurrence. There's a function in this Maple. And then you can bring out this left-hand side of the identity, satisfy this recurrence. And then you only need to plug in the right-hand side, whether check this is satisfied the same recurrence or not. Then you're done. So, and because once you believe this is true, you already try some initial values. Otherwise, you will not believe this is true. So this is the proof of this T-shirt. I hope after this, people will remember this identity. And more, if some student here or if people not familiar with WD method, I highly recommend people to read this nice book, A equal to B. So almost every my student have one of these books. So, okay, that's a quick overview of WD method. Now I come to my about the vanishing sums. I forget when I start my talk is 20. Okay, I think I still have 10 minutes, right?
Yes.
Okay. Now let me see how we can use the residues. I think this is starting from my conversation with Peter Pauli. And he, in 1995, he did a lot of work about the rational summation, which is about how you take sum of rational functions. And he always feel disappointing about this work because he say, in this rational summation, there's not so many interesting applications. And I think finally, last year, I found some nice application of rational summations. So which has something, how we can prove vanishing sums. So let me first recall the classical residues, which is for rational function, this can be defined very algebraically. So for any rational function, you can always compute the partial fraction decomposition. And the residue of this rational function at the pole of alpha I1 is just when j is 1. So this is called the residue of this rational function. So this coincides with the usual definition in complex analysis. And the nice thing of the residue is you can use this residue to view this as abstraction of a rational function to be integrable. So if you want to test whether a rational function is derivative of another rational function, the necessary condition is you only need to check whether all the residues are 0 or not. So, and if this G exists, we will say F is integrable. So this is if something is integrable, and if and only if all residues are 0, which means residues are abstraction for a rational function to be integrable. And now let me do a discrete analog of this. So in almost 10 years ago with Michael Singer, we introduced so-called discrete residues. And discrete residue is not defined at a pole, it's defined at an orbit. So for a complex number, the z orbit is quite natural. You just take this set. This is this is called the z orbit. Now you do the partial fraction decomposition according to these orbits. So you can find this partial fraction decomposition where those beta i's are in different z orbits. And then we define that for at the orbit, you sum all those residues over the one orbits. So you take this, this is the sum of the usual residue at the orbits, but then now you take into account the multiplicity. So it's in the classical residue, you only need to think about the multiplicity 1. So here you need to take all the multiplicity. So this is so-called discrete residues of this rational function. So now you have a bunch of residues, which is summing over usual residue over the one orbit. The nice thing of defining this kind of residue is the following. So there's a discrete analog of another integrability problem. Given a rational function, you want to detect whether this rational function is the difference of another rational function or not. This is the discrete analog of previous problem. And then we get a nice necessary symmetric condition is the following. So F is summable if and only if all the discrete residue is 0. So which is kind of exactly the discrete analog of a previous vanishing theorem. Let me take one simple example. For instance, this rational function, all roots are in the same orbits. This is in the same 0 orbits because they are different they are in the same orbits. And then you do the partial fraction decomposition. And then the discrete residue is just sum of those usual residues. And you know that this is the 0, so which means F is summable, which means this rational function can be written as a difference of another rational function. You just look at the residues, then you can detect this global property. Okay, there's
Shaoshi, there's a question. What is Christoph asks, what is B of beta?
Beta is the root of the denominator of B. So B is a polynomial, and then beta is the roots of this polynomial.
Okay.
And then you separate all those roots according to different orbits. So.
Okay. Thank you.
Okay. Now let me go back to the. So now the question is how you detect a rational function is summable or not. Let me start from very simple, just a very monomial case. So for monomial, actually there are some, when we in the calculus, we learned that any kind of this monomial can be written as the derivative of another rational function, if and only if this m is not -1. So that's a very common knowledge in calculus. How we can get the discrete analog of this result? So we need to introduce so-called the falling factorial, which is analog this multiplicity m power function. So which is defined as following. For m is positive, this is usual falling factorial. When m is negative, is defined in this way. And then after this definition, then we can get a nice discrete analog of this result. It's almost the same, just replace the m by m over lower bar, and then everything and replace the derivative by shifts. So we get the same result for the if and only if m is not -1. Almost the inside is almost the same. So this is for this kind of monomial terms, we know how to detect the summability when n is -1. There's a very nice, very old result due to Nicole in many 300 years ago. And he wrote down a very nice family of summable rational function. So it's of the following form. So you first take this denominator. So those beta 1 to beta n are in the same z orbit. And the numerator px has degree less than the denominator by 2. So because the denominator has the degree n, and then the numerator has degree less than the numerator by 2, and then he claimed that this family of rational must be summable. So this is the Nicole's family of summable rational function. And what he's proved is the following. So he write first you need to compensate the denominator so that this is become a falling factorial. You just add some, if there's some terms, you just add some and then also put something in the numerator. Then you can normalize the denominator like this. And then after that, you write the numerator in terms of this basis. Actually, in some book, they say you note that this Ci actually is the Stirling number of second kind. Actually, so which means the Stirling number of second kind was appeared earlier than Stirling. So some people say this should be called Nicola's number, but that's the historical problem. So, and then after this, then you can compute this one, and then you use the previous monomial criteria for the summability. And because this is less than minus n minus 2, so you know that I minus n must cannot be equal to -1. So you prove that this is summable. So this is the Nicola's original proof. And we can also give some complex analysis proof. I will not recall this classical residue because I think everyone knows this result. Okay, let me just recall that if you have a rational function with the numerator has degree less than the denominator by 2, you can show that the residue of this rational function at infinity must be 0. That's the complex analysis. Now you can use this factor to prove this Nicola's theorem using this classical complex analysis result. In order to prove that this is summable, because they are in this only one orbit, so you only need to check whether all those sum is 0 or not. And then you can write this sum, and because this is the at the finite place, so this is the sum is equal to the negative of this residue at the infinity. And then by the calculation, you show that this actually the residue at the infinity is 0. So you prove that this sum is 0. So you show that this is summable. But anyway, that's the different proof of this. Maybe a little bit complicated, but not so complicated, but it's still technical. So let me bring the one nice corollary of this Nicola's result, which is leading to vanishing sums. So vanishing sum is like this form and RK. And where RK, you can now start from any polynomial with this degree conditions, for instance, and then you can compute this expression. Then you can show that this sum is 0. So the proof is you just write down this rational function, and then you apply this Nicola's theorem, and then you think about this discrete residue. This is 0, so this is. But let me take one example of this, how this corollary become interesting. If you choose a nice P. Let me see how we can show this vanishing sum. And then this is the kind of idea to prove some identity. You only look for some rational function, like Doron's the paper with Wilf say rational function certify combinatorial identities. Here is the same idea. To prove this vanishing sum, you only need to construct the following rational function. So this is the rational function I have, this one. And then you can extract this. We need some method to construct this rational function, but we have the algorithm to compute this. And now you only need to check that because this degree is 0, so this is less than this. So now you only need to verify that the residue of this rational function at the pole 0 -1 to -n is equal to this one. Then you prove the identity. And indeed, you use the Lagrange formula. You can see that the rational function of this function at -i actually is equal to this summand. Then by Nicola's theorem, you automatically get this vanishing sum. So to prove this vanishing sum, you only need to construct this rational function with this Nicola's condition on the degree. So this is a simple example. More complicated example is like this. For this vanishing sum, now the idea is also you need to construct a rational function, which is this form. And then you can see that the degree of the denominator is n plus 1. And the numerator degree is n minus 1. And this rational function satisfies the degree condition in Nicola's theorem. Now you need to show that this summand actually is the residue of this rational function at -i. And indeed is this one. And then you prove this this vanishing sum. So to prove this vanishing sum, now you only need to construct this rational function, satisfy this condition. And then we playing this kind of similar idea for all the vanishing sum in the Gordon's combinatorial book, and all examples works well. So, and there's one so the general idea to use this idea is to find this rational function. So now the question is how I construct this rational function satisfy the degree condition. The idea actually is quite natural. You start from this vanishing sum, and then you put the x plus k in the denominator. And now you think about this rational function. And then you take the common denominator. So the numerator must be a polynomial in x. Also has something to do with n. Now the question is, you need to prove that the rational, the numerator has degree less than this one, n minus 1. Then, so because the denominator has the degree n plus 1. So you need to show this one so that you have the Nicholas condition on degree. Now the question is how you can write down this p and x. In general, you can, for the previous two examples, I write down this p and x explicitly. But in general, you can only find the linear recurrence for this polynomial sequence. For instance, for this example, the summand is of this form. And for this one, I cannot write down explicitly this polynomial sequence. And the only thing I can do is using the collinear telescoping, I can find a linear recurrence for this polynomial sequence, which is this third order with this coefficient of polynomial in n and x of this degree. And then use the mathematical induction, I can show that the degree of this one is indeed less than 2n. And note that the denominator has degree 2n plus 2. So this satisfies the Nicholas degree condition. Then we prove this vanishing sum. So for this example, it's more complicated. You need some computation to do this. And also because in Nicholas theorem, you can take any polynomial just to satisfy the degree condition. So why not you can choose some, you can take this denominator, you can take some orthogonal polynomials, and then you can cook up some nice identities like this. Because you can always take some interesting polynomials, and then you use the Nicholas theorem, you can cook up many kind of polynomial vanishing sum what you like. So this is one I tried. You can use the Lagrange polynomial to get this double vanishing sum. Usually it looks more complicated. Okay, I almost finished my slides.
Question. On your previous page, you checked it for alpha 0, the basic Lagrange, and have you tried other powers?
Yeah, I have shown other. You can get many identities because here in Nicholas theorem there are no other explicit constraint on the coefficient, just the degree condition. So that's the nice of this older result, because they are only about the degree, and then you can just choose some polynomial with the degree, satisfy this degree constraint. Then you can get some. Then you write down this. You need to do some residue calculation. Then you can get this vanishing sum. So that's the philosophy of getting a rational function to certify some value. But this is kind of inverse engineering somehow. But this you can use to cook some new identities. Okay, let me, but not for this idea sometimes didn't work for some identity. For this one, you need to do some creative thing. So we can do something like in the telescoping thing. You cannot get this, but you can create some vanishing sum. For instance, for this one, this is not a vanishing. This is a non-zero in general. But the idea is for the right hand side, you can use this first order operator to make this vanishing. If you apply this to left hand side, this is vanishing. So now you only need to check whether you apply L to left hand side is vanishing or not. And we do some calculation when you apply this L to the this left hand side, you do some simplification, and you end up with this one. But for this one, we can use the vanishing techniques, Nicholas theorem applied to this, and you can show that this actually vanishing. So you prove this identity, even though this is not a vanishing sum. But then you need to construct some L. But you can motivate this L by the right-hand side. Note that this summand k to the n actually is not holonomic. You cannot use the W method to verify this, because W method is typically very good for the holonomic input. For this one, you may not work. Okay, that's almost end of my talk. I think I go over by 2 minutes. So let me summarize my talk. So sometimes I learn from this lesson. Peter Pauli told me there are not so many interesting. He was kind of disappointed, and we are also. I think he tried hard to. In 1995, he has a very nice paper about the rational summation and the GFF factorization. And I think finally, for so many years past, we have found really some nice application of this rational summation. So this is so this lesson, we learn from this. Sometimes we need to look forward, not just look forward. We need to look backward. Maybe some older guys has some nice result. We can use it. So this is the Nicholas result. He bring us a nice family of summable rational function, and then this immediately leads to infinite many actually vanishing sums. We can use this to prove some vanishing sum. Also, you can discover some, because you can take any polynomial, just satisfy these degree conditions. So you can play with these things. But now for the future work, I'm now working on to generalize this Nicholas summable family, because maybe you can choose some different denominator, and then you still have some nice. So now we are trying to write down the more different family of this kind of summable family, because each summable family, if you take the discrete residue, you get the vanishing sums. Thank you very much.
This was really fascinating, that something from more 300, by the way, a mistake, it says 300 years ago, it's 304 years ago. It's really impressive that you got it out of its obscurity, and I never heard of Nicole. So, but this is another exciting prospect. As a simple example, you mentioned the sum of the alternating binomial coefficient is 0, and there's a famous, very elementary, where I give to my students the first time about bijective proofs, about proving it with a bijection. So of course, yes, if n is odd, it's by symmetry, but in n is even, it doesn't work. But the famous involution is you look at all the subsets. So you look at n, the largest element. If it belongs to it, take it out. If it doesn't, put it back. So this is what's called a killer involution. So each of you more complicated sums suggest at least a monthly problem and probably a paper to get a nice, elegant involutive or bijective proof. For example,
I have an open question.
So to give a commentar, an involutive, find the so-called killer involution between k even and k odd. So it'd be really interesting, and be even more interesting if you can mechanize it and teach a computer how to bijectify your proof to make it a nice bijection. Thank you.
Right. Thanks for the nice remarks. So actually, I have an open question. Can anyone give a bijective proof, like using inclusion exclusion principle to prove this side? And because usually in combinatorics is if you have alternating sum is vanishing, and there sometimes has inclusion exclusion proof. But I didn't find any. I found some of this inclusion for some alternating sums, vanishing sums. But for this one, I didn't figure out how to prove this because there's something in the denominator, and I will be an open problem if anyone can have a combinatorial proof of this vanished sums.
Yeah, beautiful problem. By the way, is it an integer, the summand?
Yeah.
Oh, okay. So that's a very good question. Thank you.
Question?
Yes, Teddy, go ahead.
Yeah. In this program that you have, in a sense, you're assuming simple poles for the analytic function f, for the meromorphic function f.
Yes.
If you have double roots, can you modify this?
Yeah, that's exactly my ongoing work with my co-author Rong-Hua Wang. We are now putting the multiplicity here because the discrete residue, the definition works for the multiplicity. Yes, indeed, right. Yeah, and then we get the more complicated vanishing sum, but still we can cook up some vanishing sum by this generalize this Nicola's family. So we are now exactly what I think is a good suggestion. Put the 2, 3 here, and then you get the more interesting things. But sometimes it's complicated, like Christopher says, sometimes ugly because summand is very complicated, and your summand is equal to 0. But sometimes I play with this. You're right. Yeah, that's actually my ongoing work with Rong-Hua. So
one possibility could be that if you have beta 1 and beta 2 are identical, then you can include an artificial parameter like epsilon and make them distinct and take the limit.
Oh yeah, that's also actually there's actually more. So this actually, there is actually, I think the result in my talk actually is kind of very elementary because there's a more advanced technique using residue by so-called Igor-Chev's method. I think their residue approach is much more advanced. But what I use here actually is kind of very elementary. So, but I still, even though it's elementary, but still interesting. So. But now I think I view as this is the way we understand why this is become 0 sometimes. So that's what I say. If you have combinatorial proof, that's nice. But actually, in my opinion, so now I have the understanding of this vanishing because this is something in terms of residues and residues in final place and something. So now I have some kind of a geometrical understanding of this vanishing. But maybe people don't buy this, but I think I'm not happy with this vanishing because I understand it from this older result. Even though I need a Zeilberger's method criterion to compute this complicated recurrence. So this is, but I understand this vanishing now. So that's probably maybe understanding is much more important than proving. So. Oh, maybe if I have a few seconds, I should advertise my another talk. So actually, this talk is not the end of the. Now I put this piece of work into more general, larger project. So with so-called holonomic polynomial sequence, you see that those P and X actually satisfy linear recurrence. So that's why now I start to work on more general. Object, so-called polynomial sequence satisfy recurrence. This is typically the orthogonal polynomial satisfy 3-term recurrence. So that's one of the special case of this. And then the question is, if you have a polynomial sequence satisfy linear recurrence, and then how you can start, how degree grows, because. And then the nice thing that for this family, actually, if you put those two first few initial, this is hops. This actually is a very nice flower, which make your beer taste better. This is, I don't know, people know this English word. Maybe I actually look up the dictionary. Indeed, this is the English word. So I'm now happy with this flower because actually it's the flower which you make put into your beer. So that's why now I kind of have a nice project which is about the beer and this flower. So I have a serious work now because the first question is about degrees growth, and indeed there's a deeper result. So we now have some very nice close connection with number series people. So I think we get more results in this, even though it's motivated by this one. So we motivated by this because this is a polynomial sequence. Now I needed to understand this degree, and then now I started more general polynomial sequence. And then I needed to understand the degree growth pattern. So just a remark, sorry.
Yeah, no, I just wanted to comment. So Cyril has put on the chat, Doron was asking, who is this Nicole? So Cyril has put on the chat that this is a Frenchman.
Nicole is a French mathematician. So he's the person who first write the first book on finite difference calculus. I think people know the Boole and Jordan's book on finite difference books, but actually Nicole has the very early books. Even you see almost not far from the invent of calculus. So this is the first book. So I think I cited this book here. Sorry, probably this.
Yeah.
It's a French book. And then there's a nice paper about Nicole. If you can look up Nicole, and you can see there's a paper about people work on the history of mathematics who has a nice paper about Nicole. And he argued that the study number of second should name after Nicole, but yeah, indeed.
So Chen, I have a question, one last question. And on your last slide, very last slide, the last formula that you put, I can give you a counterpart of this for the even case. If you replace 2n plus 1 by 2n, and if you replace the bottom by n plus k at the bottom, n plus k,
n plus k,
and the odd becomes even to n there, and that sum equal to 1. You can try to prove that.
Oh, okay. Oh, nice. I didn't. I found this in the Gordon's book, but I should also. He has a family of. Indeed, he give a family of this kind of identity, which is only one for this parameter is equal to 0. That's why I look at. Okay, maybe that's the.
I just calculated that. Okay.
Oh. Well, yeah, that's very nice. So I will look at this more carefully. So thanks for.
Okay. I think we're really out of time. So let's thank Shaoshi again.
Thank you very much.
Thank you. Oh, I had a question.